We now look at some methods to estimate state of charge that are simple methods that might be the first things someone would think of when they went about trying to estimate state of charge. And there are pros and cons to these methods. As I said, they're simple. That's a huge advantage, but the accuracies tend to be quite poor. So I'm going to call these poor methods. There's poor methods that are based on the voltage primarily, voltage sensing primarily. There's a poor method based primarily on current sensing. And we examine the methods, get some idea of the problems with them, and use that to justify maybe, or at least to propel us to thinking toward how to solve these problems, and an introduction to the type of solution that we're going to be looking at and focusing on in this chapter. So without further ado, let's begin. The first method that we look at is based primarily on measuring the voltage of this cell. And I remind you, in the enhanced self-correcting cell model, we have voltage equals OCV as a function of state of charge plus hysteresis minus the diffusion voltages minus IK R0. If for some reason I were to assume that all of these were negligible, then I would have a relationship that said the terminal voltage is equal to the open circuit voltage. And the open circuit voltage is something we know how to measure. We looked at that in the last course. And for some cell, the open circuit voltage relationship might look like this. This is the state of charge axis. This is the open circuit voltage axis. So the approach is very simple. The approach says I measure a voltage. Now I can't measure open circuit voltage in a application, but I measure the terminal voltage, and I assume that it's about the same as open circuit voltage. So suppose I measure some voltage up here. I would go over on this curve to where that voltage intersects, and that there would be my state of charge estimate at that point in time. If I had a voltage measurement down here, I would go down here and say, that is my state of charge estimate at that point in time, and so forth. Very, very simple. Now, this curve, the OCV relationship, could be stored in a table. It could be a function. Usually what we would do, in fact, is we would draw the curve the other way, which looks like this. And this is OCV in, and this is SOC out. I just switched the axes. And so if I measure a certain voltage, that allows me to directly compute from it what the state of charge must be. So, very simple. Doesn't work. Why doesn't it work? Well, we're ignoring hysteresis. We're ignoring the diffusion voltages. We're ignoring the I times R term. So there's a lot of uncertainty in this relationship, which amounts to noise of one sort or another. Maybe not purely random noise even, but some disturbance, some noise that we're not taking into account when we do this estimate. Another issue is, suppose I were to make a measurement right there and notice that with some error on this measurement, a very small voltage error causes a very large SOC estimation difference. So because I know my voltage is not OCV, I know there's going to be noise on this axis. That's going to cause a huge difference sometimes in the state of charge estimate produced, and the accuracy is going to be very poor. So on the flat areas of the curve, which become vertical areas when I flip the axes, we get a dilution of the accuracy of the estimate. We get a poor estimate. There's a modification that we can make to this method that is actually quite simple. Hysteresis is kind of challenging because, first place, we don't have very good models of it, and even if we did, we'd have to somehow simulate that model or estimate that model of hysteresis. So we're still going to assume that's negligible. Diffusion, same kind of thing, we'll assume that's negligible. But we will retain the part of the model that says voltage equals OCV minus IR. We'll retain that part. And then I can do, so if V equals OCV minus IR, then I have V plus IR0 equals OCV. And this here is a modified voltage that if I invert both sides of these equations, if I put them through the OCV inverse equation, if you will, I have OCV inverse, that's not 1 over, that's the inverse relationship of V plus IR equals Z. So instead of putting my measured voltage in this axis, we are replacing that with VK plus IR0. I was not ever actually putting OCV in before. I was putting V in, pretending it was OCV. Now I'm putting in V plus IR0 instead to at least account for the ohmic part of the voltage, and that helps a lot. It really does, but it's still pretty awful. I call this the Tino estimate. My recollection, although it's been so long, was the first time I heard of this was a report from Nissan. They had a vehicle called the Tino electric vehicle many years ago. It was in the 90s, and this is how they would estimate the state of charge on that vehicle. Obviously, things have improved a great deal since that time. To give you an idea of how well or how poorly this approach works, I have a result here. I hope you can see the colors. In this plot, it was a very long test. It was over, almost 500 minutes. So it's like 8 hours, I guess, of testing. And the state of charge was calibrated at 100% at the beginning of the test, and after the test, calibrated also. And I executed a lot of dynamic profiles on the cell. So each one of these things here indicates the period of one dynamic profile. And I think it was a UDDS test. It was so long ago, I don't remember all the details of it. So that green line that I circled parts of is the true state of charge of the cell versus time, as accurately as I could determine from the lab test equipment by calibrating the beginning point, calibrating a 0% point over here, and Coulomb counting, as we'll see what that is in the next section, using the accurate current sensor on the test equipment in between to get the estimate of what I called the true SOC. That's the truth. The blue line, which is the SOC estimate line, which is underneath it, is the Tino estimate of the state of charge. It's when I look this up on the OCV versus SOC curve. And obviously it's far worse, far worse. So when the state of charge up here is actually about 60%, it's saying, it would have to zoom in to see exactly what it's saying, but it's somewhere roughly between 30% and 85% is the SOC range in that interval right around that point when the SOC really hasn't changed much. So a pretty poor estimate. We can do some, if you're a signal processing person, you'd say, well, yeah, it's noisy. That's fine. We just filter it. So we design a low-pass filter. That can help. It adds delay, though. There's group delay that's added whenever I filter a signal that I have to account for. So basically, the filtering will allow me to predict or estimate the SOC in the past, but it doesn't really allow me to estimate the SOC right now with any accuracy. There's phase distortion too. I'm not sure that's such a huge deal for this application as it would be for something like a signal processing application where you're listening to it and the phase is something you can hear. I think basically the delay is the bigger issue. So Tino estimate by itself is not good, and if I didn't do the IR correction, it would be far worse. It would just be pegging the limits between 100% and 0% almost the entire time through this test. And we get a very poor estimate. You're going to do a homework project, and I don't remember if I'm going to use this exact same data or not, but you're going to get a result very similar to this if it's not even exactly the same result. So you can implement this and try it and see how well it works. So Tino estimate, voltage only, or voltage with a small modification based on measured current, does not work too well. But we do find, interestingly enough, we do find an application for the Tino estimate in the next chapter of notes. It's not really for SOC estimation directly, but it's going to help us with our parameter estimation to ensure robustness of our parameter estimator. So that's an interesting result. We'll see then. So you say, okay, well, if voltage by itself, or essentially by itself, is not a good way to estimate state of charge, let's look at what else we have. Now, temperature, not really. Current, yeah, maybe current would be a good way to estimate state of charge. So what we're going to do is we're going to take the state of charge equation, and we have this equation, and it's correct. So Z of t equals Z0 minus 1 over Q times the integral from 0 to t of, we'll put in the eta there, eta of tau, I of tau, d tau. That equation is fine. There's nothing wrong with it. And we use that as the basis of our estimator. Whenever we have an estimate in this chapter of notes, I'm going to use a hat on top of it, this symbol here. So Z, this is the true state of charge, but Z hat is my computed estimate of state of charge, in this case at time 0, and in this case here at the present time now, time t. And I take the Coulomb counting equation, which is true, and I replace it with the Coulomb counting equation that I actually implement. So over on the left-hand side, I used to have a Z of t. I now have a Z hat of t. I'm estimating state of charge right now. I used to have Z0. I now have Z hat of 0. I'm estimating what the initial state of charge was when I started my battery pack. I've got 1 over Q. Well, I don't know Q exactly, so I have 1 over Q hat. That's my estimate of capacity. Here I have eta of tau. I could actually put that in here. So eta of tau, that would be fine, except it's really hard to measure Coulombic efficiency with any accuracy, and it depends on the current and state of charge and a bunch of other things. And it's so close to 1, it's usually about 0.99%, 0.99 or 99%, somewhere around there, that, I could put a number in there and it might help. That's fine. That's not really what we're focusing on here. And then finally we have I of t, which is the true current experienced by this cell, and over here I have only knowledge about what I measure. Now, I say that because what we measure is not necessarily the same as the true cell current. So measured current is true cell current plus some measurement noise, plus some measurement offset. There may be a constant bias in the measurement, plus whatever nonlinearities there are in the analog to digital converter at that measurement interval. There's also self-discharge current, which is, maybe I should subtract that, but anyway, I'm just adding the effect of self-discharge current because that is truly experienced by the cell, but I can't measure that. And also, and this can be pretty significant, we'll see when we look at cell balancing, when I have all these cells together in a battery pack, and I've got some integrated circuit over here that is making measurements, this integrated circuit is often powered off of a set of these battery cells, and there's this I leakage current that powers the integrated circuit, but is not what I ultimately end up measuring down here when I'm measuring battery pack current. And this leakage current can be in the order of milliamps, which might not seem like a lot, but if you do that for a long period of time, it makes quite a difference. So, when I'm Coulomb counting, what I find, and what you'll find when you do the project, is that if my initial state of charge estimate is wrong, there's nothing in this equation that with any feedback to tell me that it's wrong, and the equation that computes an estimate of state of charge now is never able to correct for an incorrect initial estimate, and it's always wrong. Unless by random chance the noise helps, but we would expect it always to be wrong. If my initial if my capacity guess is wrong, suppose I guess a capacity that's too high, well, then my state of charge doesn't change as fast in my estimate as it really does in practice. Or if my capacity estimate is lower than truth, then my estimate will change more quickly than truth. And again, there's no feedback. There's no way of finding out that my state of charge estimate is becoming poor and to do anything about it. With the current measurement, if I start out, even if I start out with a perfect state of charge estimate and a perfect capacity estimate, this noise here is going to cause the integration of that noise to be something that that people who study random processes call a random walk. And on average, we expect the integral of I measured to be the integral of I true. But if the truth does something like this, the estimate is going to do something like this. It's going to walk randomly around the truth. And if we look at the error bounds, which we can compute with some assumptions, if we look at the error bounds grow. And they never shrink down again, or they never achieve a steady state. And again, there's no feedback to tell me what noise is doing when I integrate it here. And so my uncertainty just grows and grows and grows. Integrating a bias is awful. So if I have a bias in my current sensor, when I integrate that, it becomes a ramp. So my Coulomb counted SOC estimate gets progressively worse over time. The nonlinearities are harder to characterize, but you might even think of them as noise, and they might have some effect, something like this. Self-discharge would be kind of a negative bias, and leakage would be kind of like a negative bias also. In any case, Coulomb counting is correct in the sense that that is the equation that describes state of charge and how state of charge really truly works. But to use that as the only basis for estimating state of charge has lots of problems, and we've discussed some of them here. So we could say that Coulomb counting is okay for short periods of operation when all of these other impacts, the noises and so forth, don't really have time to accumulate big errors. So it's okay for short periods if the initial conditions are known, or if I can frequently reset the Coulomb count. So if I have a way of calibrating my Coulomb count on a fairly regular basis to start over with a new Z0 right now and to then use the Coulomb counting only for short intervals, that's okay. It can be okay. Maybe not great, not the best, but okay. And there are some cells for which this is really the only feasible way of doing SOC estimation, unfortunately. If a cell has very, very flat OCV characteristic, that means that voltage has almost no information in it regarding what is the state of charge. I keep on mentioning feedback because I'm trying to make you think a certain way. Our state of charge estimator that we come up with that we'll call optimal is essentially Coulomb counting with feedback, and it uses voltage as feedback in order to improve the estimate. If voltage has a lot of information, so if my OCV relationship of a cell is fairly slopey, that means that even a noisy estimate of voltage gives me a fairly decent estimate of SOC that I can use to help as feedback. It's not perfect, but it's a noisy estimate that I can use as feedback on my estimator. That's great. But if my cell has a very flat OCV curve, then I get a very noisy SOC feedback, and the methods we'll look at, the feedback methods, don't work as well as we would hope. So for certain types of cells, particularly iron phosphate that have this flat characteristic, sometimes Coulomb counting is about the best you can do, and you're essentially running open loop unless you determine that, oh, I'm operating over here or over here, so I'm very nearly fully charged or fully discharged. Then voltage gives me a lot of information about SOC. Then I can reset my Coulomb count and keep on going from there. So that's kind of a band-aid solution. I don't care for it myself, but I know that that is implemented in some real battery management systems. one of the issues is I don't get any feedback at all until I'm almost at the very edge of operation, and that is a big concern because my SOC estimate might have been significantly wrong, thinking that I had lots of power available, and then I get an accurate update that says, oops, make a huge adjustment right now to say that there's no power available, and that would be very, very bad in application. So if I have a cell with an iron phosphate positive electrode, this is very flat. Furthermore, but iron phosphate is great for aging. It's almost impossible to kill these things, so people love them and they're cheap and so forth. So they're great, but they're also very hard to use. Similarly, if we have a LTO negative electrode, which is lithium titanate oxide, it has a similar extremely flat characteristic. It's great. It's almost impossible to kill an LTO cell. They've got tens of thousands of cycles with almost no degradation. They're fantastic cells, but for control purposes, very, very, very hard to know what your state of charge is because of that. In any case, if it's possible, if voltage sometimes or frequently gives me some indication of what state of charge is, I can reset my Coulomb count and use that as a basis of an estimator. Also, with modern standards that are coming out for vehicles, for redundancy purposes, manufacturers are beginning to depend on more than one state of charge estimator, so that if one of them gets very confused, the other one hopefully is not as confused, so you'll at least know there's a problem. If you have two state of charge estimators using fundamentally different methods of operation, then if they agree, then you assume that they're both right. If they disagree, then you assume that at least one of them is wrong, and that might cause you to implement some safety sequence to make sure that everything is okay. So you still might use Coulomb counting as one of those methods, especially if you can reset it, but hopefully you use the more optimal methods we'll talk about in the rest of this chapter as the other method, and that would be your primary method. So I keep talking about feedback. We want to use current and voltage. The current-only approach doesn't work. The voltage-only approach doesn't work very well. But those are the only sensors I have. So I need to use both. I need to find a way of using current and voltage together in a feedback situation to come up with a better estimate. And this is what I call model-based state estimation. There's a lot of variations on this. We'll talk about one kind of family of this in this chapter, but if you look at the literature, there's actually quite a bit of it out there right now on how to do state of charge estimation, and all of the best methods use some kind of model-based approach. And the idea is very simple. You could explain this to someone non-technical, I think, if you were patient and chose the right words. The idea is I can look at what goes into my box, my true system. In this case, this is the battery cell. I can measure the electrical current that is the input to the battery cell. And this is I measured. And I can measure the output from the battery cell. This is V terminal, the V measured. At the output of the battery cell, and I'm trying to figure out what is going on inside. What is the internal state of this battery cell? Well, the approach that we're going to look at says, let's use a bunch of equations. Let's use a model that describes how the battery cell works. We'll measure the current, and we'll put the current into my model. Now, everything above the line is hardware or reality. Everything below the line is software. It's my program. I measure current. I put it into my model. In other words, I simulate one time step of my model. And because my model is being executed in a program, the state is simply a variable in my program, and I can do anything I want with a variable. I can print it. I can save it. I know whatever you want you can do with the model state estimate. And if this is all we did, by the way, this is Coulomb counting so far. There's no feedback yet. The measured current goes into my Coulomb counting model, and I update my state of charge estimate, and who said that doesn't work? The difference between that and what we're going to do is that we are going to then go one step farther and say, based on my model state, I'm also going to predict a model output, which is a V hat, a prediction of the voltage that I'm going to measure. And then I'm going to compare the predicted voltage to the actual voltage, and there's going to be a voltage error. I use a tilde symbol when I talk about error. So that's a voltage error. If the voltage error is 0, I probably did a great job of predicting the state, because we agree. If the voltage error is not 0, there's a number of reasons for that, which we have to think about. But the voltage error is going to come back in, and it's going to adapt the state estimate in my model. It's the feedback. That's the feedback we're going to use to adjust slightly the model state to hopefully make the model state stay closer to the true state, and even converge to the true state in a best of possible situation. Now here, there's something called process noise. Process noise impacts the true system state, but does not impact my model state. This is like self-discharge. This is leakage current. In a negative sense, it's the noise on the measurement and so forth, which actually does impact the model, but not the true system. But we can basically lump it together with the noises going into the system for our purposes. So there are things affecting the true state that I don't know about, and furthermore, there's things affecting the measurement that I don't know about, the sensor noise, and even some modeling error we could put in there. So there's uncertainties in the model, there's uncertainties in the measurements, so I don't want to rely extremely heavily on this error if I know that there's a lot of these noise uncertainties. I want to use the error, but I want to use it very carefully. On the other hand, if I know that the noises are small or non-existent, then I want to use this feedback error very aggressively. So the algorithm that we've come up with is very intelligent in how it uses this feedback estimation error. Well, that's what we say here, I hope. Measured and predicted outputs are compared. The error between them, that's the V tilde error, is used to update the model's estimate of the true state. That's in my software. The output error, this V tilde, is due to state errors. My estimate is wrong. Measurement errors. There was some sensor noise. Or model errors. My model was wrong, not quite right. And so we have to do the feedback update carefully to account for all of these, but we do know how to do that. So under some very specific mathematical conditions, there's a technology called the Kalman filter, named after its inventor, Rudy Kalman, back in 1960-61, which is a special case of something I'm going to describe in a minute called sequential probabilistic inference. This Kalman filter, under these specific conditions, can be proven without, mathematically just proven to be the optimum internal state estimate of the system, given noisy measurements and so forth. So that's great. An optimum is nice. I can probably show you a million things. No, I can't. I don't know that many, but there are a lot of things that are optimum on paper, but really don't work at all in practice because the conditions, the assumptions that are made when coming to the optimal solution are poor assumptions. But in fact, the Kalman filter has been used for 5 decades now, more than 5 decades, and it continues to be used because it is so robust. Even when these these specific conditions are not met exactly, and we will not meet them exactly, but when these specific conditions are not met exactly, the Kalman filter is no longer the optimum state estimate, but it's a great state estimate, and it's very robust. It works in practice, and these are used all the time in lots of applications. They're used in navigation and target tracking. They're used in aviation. They're used in your GPS that you have. They're used just all kinds of different places because they work so well. So we're going to apply them to the problem of estimating a battery state. The Kalman filter was derived for model equations that are linear equations. We'll start by looking at that ourselves, but the battery model that we are using is not a set of linear equations. It has nonlinearity in it, so we will look at some variants of the Kalman filter that work with nonlinear models as well. Just in case you're curious, if this is something you go through this chapter and decide, wow, this is exciting to me, we have a whole course, ECE 5550, which is called Applied Kalman Filtering, and the entire and only subject matter of that course is exploring all the nuances of the Kalman filter and depths of the Kalman filter and different applications of the Kalman filter. It's a great course, and there's lecture recordings available too if you're interested in looking at or viewing those. We'll start looking at the Kalman filter, I guess, right now. The Kalman filter depends on some background subjects that may not be fresh in your memory. So before we get too deep in the Kalman filter, there's going to be a review of some of them, and especially probability, because probability is one of those subjects that takes a few looks at it to really understand it well. And even if you've seen it before, I think that you will benefit from looking at it one more time. But probability is important because probability is a deterministic way of talking about something we don't know. It quantifies what we don't know. And we don't know what the modeling errors are. We don't know what the noises are. We don't know a number of different things in the problem that we're discussing. So we use probability theory to quantify what we don't know, and then we can work with that to come up with an optimum estimate of the state of our system, even though we don't know things perfectly. We just use our quantified unknowledge, uncertainty, to guide us. So we are going to start by thinking of the battery state of charge estimation problem in a completely generic context. Completely general context. Doesn't have to be a battery cell at all. This could be estimating the position of an aircraft using radar measurements. It's the same ideas would apply, but we're going to use a battery model. Kalman filtering, or sequential probabilistic inference, which is the general field in which Kalman filtering is one answer, assumes that the system whose state we are trying to estimate is modeled with a set of equations that look like this. So present state is some function, possibly nonlinear, possibly linear, some function of the prior state, the prior input. So U here is the input for us, think battery current, and W is a process noise. This is something that is input to the actual system, like a self-discharge current or a leakage current. So the actual system experiences this input, but we don't measure it because either we can't or we decided it was too expensive to measure it. So there's two inputs. This one is the one that we measure. That's called the deterministic input. This one we don't measure. It's called the random input. We already have an equation like this. Our enhanced self-correcting cell model, if you go back to chapter 2 and review it, looks just like this. Now, we haven't talked about W, that's new, but we have a state equation that has exactly the right form to be used with sequential probabilistic inference, and that's really one reason that I described the cell model the way I did, was looking forward to how we would use it here. Then we have an output. Our system has an output yk. This is whatever we measure from the system, which is some nonlinear function of the state of the measured input and sensor noise. Now, there's room for confusion here because we're going to start using V for two different purposes, and I'm sorry about that. V is the standard symbol for measurement noise in this literature. So I decided to adopt it, even though I know there could be confusion. But we're going to talk about Y now as being the cell output. Y is now the voltage, and V is now sensor noise. I didn't really know any good way of avoiding confusion one way or another. F and H are functions. They could be time varying. I'm not going to put the time dependency in the equation. It could be nonlinear, as we mentioned. They're just descriptions of how the state progresses over time and the output is computed. And again, the ESC model is in this form already. Sequential probabilistic inference then uses a model like this and says there's things going on in the system that I cannot directly observe. For example, the progression of this state from time step to time step, but there are things that I can observe. I can observe the voltage measurements. So the sequential probabilistic inference problem says I want to estimate the present state, xk, k being now, of a dynamic system using the set of measurements. First time we've seen this fancy y, but what this means is the fancy y is all measurements at the output of the system from time zero all the way up into right now. So I'm not relying only on the present measurement of voltage right now. I, in fact, am using somehow all of the voltage measurements I've made up until and including time now, and furthermore, well, I don't say it, all of the inputs to the system as well. That's kind of implied. We're also using UK, which is U0 all the way up to little uk. So this is trying to be a fancy U. The picture may be helpful, showing with the dotted line there's things going on under the surface inside of our system that we can't observe. And so we have the state going at time k minus 2. The real state is xk minus 2, and at k minus 1 the real state is xk minus 1, and at time k the real state is xk. How does the state move? Well, the deterministic input u is part of it, but the process noise wk is also part of it. And wk is not deterministic. I can't measure it. I don't know it. It's unknown. It's random in that sense that I don't know it. So because I don't know it, but I want to describe it as an engineer, what do? We try to describe what we don't know. And so we use a probability density function to describe if I know, this is a conditional PDF saying, what is the probability density function for arriving at state xk, some value of xk, given that I know for certain that at time k minus 1 the state was xk minus 1. So the uncertainty here that we're talking about is the process noise uncertainty of w at time k minus 1 that is causing this to happen, and how w impacts the system and influences the system to make x at time k from x at k minus 1 and wk minus 1. So we need to describe the uncertainty of the process noise and the impact that has on propagating the state over one time interval. But even if I know for certain, and what we're drawing in these blocks, see the xk minus 2, xk minus 1, xk, those are the actual true states, unobserved but true. Even with the true states, what we do observe is the voltage measurement at time k minus 2 and k minus 1 and time k. That is also not a deterministic function of the exact state. That also has randomness in it because of the VK noise, the sensor noise in our system. So there is randomness here that is describing sensor noise, some probability distribution function of the measurement given the state itself. So this is why it's probabilistic inference, because I'm using probability theory to talk about these PDFs and to use those PDFs then plus the model to come up with an optimum estimate of the state. So using the measurements y, using the known inputs u, using these conditional probability density functions, come up with an optimum estimate of the state. So while the observations are not perfect, they do allow us to peek in and get some idea of what's happening in the true system, and based on that we estimate this state. So that's the big picture idea. Hope that's helpful to give some motivation, because before we continue we need to think about what is the background concepts to review before we can talk about optimizing anything. And this should give you a hint. That's the conditional probability distribution function. So is that. These are things that were, if you've taken only one probability course before, these were probably fairly advanced topics, and now we're using that as the jumping off point for what we're doing. So we have to review some probability theory, including just general probability theory, some conditional probability theory here, the idea of what a random variable is, what a random vector is, because our state is not a scalar; it's multiple elements that together describe the state of the system. So we have to talk about vector random variables, and then not only is this a vector random variable, but it's a vector random variable that changes with time, and that's what something we call a random process or a stochastic process. So we have to think a little bit about that. So we're going to spend a little bit of time in probability theory building up these background concepts, and once we have the concepts described at an appropriate level, then we'll come back, look at this picture again, and say, okay, now we're ready. How do we do the optimal state estimation? So that's where we're going. Hang on. Again, the details of this are challenging, but after you have some familiarity and after you've used this yourself, I think you'll gain some intuition. And this Kalman filtering thing, while it's pretty challenging to pick up a book and figure it out, once you've done it for just a little bit, it becomes really second nature, and it can make a lot of sense. All right, let's go. Let's work on some of the background concepts.